Alrighty, so I'm going to go over the rest of that worksheet that we were just looking at. So let's take a look at it here. Let me do a screen share here. So we just finished up with number 4. Now we have to look at number 5. And so number 5, we have an object with a certain moment of inertia, 4 kilograms times meters squared. And then we are given a graph of the amount of torque applied over a certain amount of time. And it wants to know what is the object's angular velocity at 3 seconds. Well, I'd like you to notice one thing is that this graph tells us that we have a variable torque. First, it starts at 0, and then at 1 second, it's at 1, and then at 2 seconds, it's at 2, and then all of a sudden it drops off, and at 3 seconds, we have no torque. So therefore, what I'm going to say is if I can find the final velocity at 2 seconds, that will be the same as the velocity at 3 seconds because the torque is no longer being applied. So therefore, I'm going to write my moment of inertia as 4 kilograms times meters squared. And let me do my stop screen share here. Okay. So I have that, and then I have my graph. I'll just draw it kind of small, but we have torque on the vertical axis, T on the horizontal, goes up like this, down, and then over. This is 2. This is 2 right here. All right, so now we have to find the final angular velocity. Well, what is the formula? What is the formula that relates torque, angular velocities, and moments of inertia? Again, it's torque is equal to the moment of inertia I times delta omega over delta t. We're interested in finding, we also know, it says it starts from rest, so we also know that the initial angular velocity is equal to 0. So I'm going to rearrange this equation just a little bit and say that my torque times my time divided by my moment of inertia I is equal to my final angular velocity. Why do I say that? Well, because first off, if my omega naught is 0, I know that my delta omega, I can say this is essentially equal to I times omega f over delta t. And I hope you can see then that you just rearrange it just a little bit and you can come up with this equation here. And so, but here's an interesting thing about this problem is that the torque varies. Do we use 1 for the torque? Do we use 0? Do we use 2? What do we use? Somewhere in between? Well, as it turns out, when you have a variable torque like that, you can sort of treat it like we did our momentum impulse problems. Meaning if I take the area under this graph, that's going to tell me what tau times t is. It's going to tell me what that value is. And so, actually, what I should do is just to make this a little more clear, I'm going to leave my moment of inertia over here, and I'm going to say that this is then equal to the area. So the area is equal to omega f times I. So therefore, our area is base 1/2 base times height. That's 2 times 2. That's equal to 4. Divide by 2. That's 2. So I'm left with 2 is equal to the moment of inertia I, which is 4, times omega f. And so therefore you can see that the, well, for this one, it's pretty easy. I could do the actual value in my head, but it's your omega f then is 1/2 or 0.5 radians per second. So omega f is equal to 0.5. That's not a 5. 0.5 radians per second. All right, so that's our answer. All right, so let's go into the next one then. Screen share here. Okay, so now we're looking at number 6. Same thing, it says use the same diagram in question 5, except for now we have a different moment of inertia. It doesn't tell us what that is, we have to figure it out. And it has an initial angular velocity now. So if we have a ring, you could think of a ring, so let me do my stop screen share here. You could think of a ring as sort of like a series of tiny masses distributed at a radial distance, an equal distance from the radius around it. So that's a terrible way of explaining it, but the point is that you can sort of approximate that as a circle with a series of tiny point masses all the way around it. Why do I say that? Why is that even important? So let me bring up the question here. Why is it even important? Because if we're trying to find the moment of inertia of something like that, so we have an object that's rotating and we have a bunch of masses in equal distance around them. And so this is a radius r. And each one of these little masses out here would have a mass of m. We can just say that then the moment of inertia itself is simply equal to the total mass of it times the radius squared. So this is why it's useful, is because if you can approximate a bicycle tire as a series of tiny point masses located equal distance from the radius going around it, your moment of inertia is pretty simple. It's just mr squared. You just add up all those masses, multiply it by their radius squared. All right, so if that's the case, then we can figure out the moment of inertia, and then we just do the same thing we did last problem. So I'm going to say then that the area, I'm just going to take exactly what we did from last time. I'm going to say the area is the same. It's still 2 because it's the same graph that we're looking at. And so the area is equal to 2, and this left side then is the moment of inertia, except for now we do have initial angular velocity. So it's not just omega f, it's delta omega, where, so this is where delta omega is omega f minus omega naught. Again, I'll let you plug these values in, but we have, so if I read that problem, we want to find omega f, but we're given that the initial angular velocity is 0.5 radians per second. And so you just plug that in, you calculate your moment of inertia, and then you just solve for omega f. And you should get a value of around 19.2 if I did my math right. So the final answer then is omega f should equal 19.02 radians per second. Never forget the unit. And so that's our answer for that one. All right, so let me do a quick screen share here one more time. We're almost done. All right, so now we have number 7. All right, number 7, we have a rod with a length and a mass, and it's rotating about one end. Because keep in mind, when we talk about moment of inertia depends on which way the object is going to be rotating. And so if you have a pivot point or an axis of rotation, say through the end, that's going to be very different than a pivot point through the center or through its axis of symmetry. And so be careful about that. It says that we're given a short but sharp 1,000 Newton hammer blow at the center of the rod, aimed in a direction that causes the rod to rotate on the axle. The blow lasts a mere 2 milliseconds. So keep in mind, we don't deal with milliseconds in our equations. They're set up so that we deal with standard SI units. So that would be 2.002 seconds, not 2 milliseconds. All right, so I want to know what is the angular velocity immediately after the blow. So let me stop my screen share here. Okay, angular velocity just after the blow. This is really like the others. It's just we're adding one more piece into it. So let me draw a little picture here. We have a rod with a certain length L. This length corresponds to the entire length of the rod. It's going to be rotating about one end, and it has a certain mass as well. And we apply a force right in the middle, which is equal to 1,000 newtons. And it wants to know what its, it wants to know what is the rod's angular velocity immediately after the blow. And I think we can assume it starts from rest. Yeah, it does start from rest, so we can assume that omega naught is 0. So we have to know first what is the moment of inertia. And so let me write my equation. My equation would be tau is equal to the moment of inertia times the acceleration alpha. The moment of inertia is equal to, for a rod spinning about its end, because keep in mind, if I ask you what the moment of inertia of a rod is, that question's sort of incomplete. You need to know how that rod is going to be rotating. And so therefore, the moment of inertia of a rod that's rotating about one end is equal to 1/3 mass times length squared. Okay, okay. All right, so then I'm going to simplify this just a bit. And I'm going to say that the torque is equal to the moment of inertia 1/3 mass times length squared. Of course, convert the mass to kilograms and the length to meters. And that's multiplied by the angular velocity, which is delta omega over delta t. And by the way, you'll see me sometimes write delta t or just t. The reason I do that interchangeably is for most problems, that you do, you can assume that your time starts from 0. And so really delta t, delta t would really represent the final time minus the initial time. But if your initial time is 0, this just turns out to be delta t, like the final time. And that's just your regular time. That's just how long it takes. Just keep that in mind. All right. But I noticed one thing. They don't tell me what the torque is, do they? All they say is that you apply a force a certain distance away from the pivot point. Well, keep in mind the way we can rewrite torque, right? Torque, I'll write over here. We can also say that torque is equal to the force times the distance to the radial arm, or the moment arm, I should say. Or in other words, another way of putting that is the perpendicular distance between the line of force and the pivot point. And so in this case, that just corresponds to the radius from the pivot point to where you're applying force, which is equal to 1/2 of the length. And so I can rewrite this as force times length over 2. Okay. And then, well, let me simplify this down just a little bit. So I'll write force times length over 2 is equal to 1/3 times mass times length squared times omega F over T. There's a little more going on right there, but we could calculate our moment of inertia pretty easily. Now you might say, like, well, why don't I cancel out the L and the L right here? And you absolutely could, but I think it's a little easier conceptually, and this is totally your preference, but I think it's a little easier conceptually to leave this in here and just calculate this entire piece right here as your moment of inertia, and then go from there. But otherwise, we have our length, we're given all these values, and so we can calculate omega F by rearranging that just a little bit. And so the answer that I get, if I do all my math correctly, is 8 radians per second. And so I get omega F is equal to 8. That's not an 8. 8 radians per second. So that should be the final answer. All right, so the last one. So let me do a screen share here, and this one I don't even have to use a board for. This is a good problem though. This is I like this problem because it doesn't have any math, but the concepts are really important. So if we look at this one, we could say, okay, so we're on number 8. It says a woman is sitting on a spinning seat of a piano stool with her arms folded. What happens to her, sorry, let me move this. Okay, what happens to her angular velocity and angular momentum when she extends her arms outwards? So I like to make the analogy with the figure skater because it's something we're more familiar with. But if you notice when you're watching figure skating that when a figure skater wants to spin the fastest that he or she can, they're going to hold their arms in like this. And then if they put their arms out like that, it's going to slow down. It's going to slow them down a little bit. And so the question is how is that possible? And why is that? Why does that happen? And the answer is all about, in fact, I had to lie. Actually, I have to use my board. The answer is all about conservation of angular momentum. Because just like linear momentum, angular momentum is conserved. There's a certain amount. In any system, there's a certain amount. If you want to get something spinning, you have to get that angular momentum from somewhere. So all systems have a set angular momentum, just like all systems have a set linear momentum. And so our equation that we would use is going to be equal to moment of inertia times omega. And so what do we have then? Well, if this number is conserved, it means it's the same before and after. So it's the same before she brings her arms in and the same after she puts them out. And so by bringing her arms out, she is increasing her moment of inertia. Why? Because the moment of inertia is a measure of how that mass is distributed. The more that mass is distributed and the farther away that mass is, or I should say, the more mass you have and the farther away it is from your pivot point or your axis of rotation, the greater your moment of inertia is. So as you increase your radius in those equations for moment of inertia, you'll increase your moment of inertia. So if this number is fixed and we've increased this number, we must therefore decrease this number. So our angular velocity is going to go down. And then the second part of the question asks, what happens to her angular momentum? Well, angular momentum stays the same because it's conserved. It's conserved quantity. So therefore, her angular momentum stays the same, but her angular velocity will go down as she moves her arms out like that. All right, so hopefully that helps. Let me know if there are any questions.